The title of my talk today is about watching the social activities of atoms. And as you see in your books, there's a handout sheet that I've given you, and there's some information written on that you might, if you're interested, want to read later on, which provides some background material, which I'll be covering in the talk. I don't think you should try to read it as I go through the talk. Now, we all know that everything, I think you all know that everything is made up of atoms, and that atoms are the smallest indivisible unit of everything around us. Now, in fact, you can break an atom to pieces, but it turns out that that aspect isn't terribly important in the world around us. It's very interesting in things like the origin of the universe and so on, but not in the things that we see today. It's the atomic nature of solids and materials that is most important. And atoms are very small. To give you an idea, if I was to take one of these, I'll be playing with these things later, one of these little ball bearings, which you maybe can see here. If I magnified an atom to be this size, I then take the ball bearing and magnify it the same amount again, this ball bearing would be the size of the Earth. In other words, the atom compared with the ball bearing is the same as a ball bearing compared with the Earth. So atoms are very, very small. There are as many atoms in a grain of sand as there are grains of sand in the Sahara Desert. So they're really tiny things. And it's actually quite amazing to look into the history of how the atomic nature of materials was discovered. It was discovered without anyone ever seeing an atom. They figured it all out before they ever saw it. But I know you guys are skeptical. In fact, you really should be skeptical. I mean, for example, I got this in the mail the other day. It says here, Professor J. Murray Gibson has won $25,000. And with excitement, I read it, but of course, I discovered pretty soon afterwards that, in fact, chances of me winning are pretty close to zero, so I threw it away. You should be skeptical of anything you see. So as a result, in the last 10 years or so, people have built microscopes that are capable of seeing atoms. And so I'm going to start off with a picture. I'll put it over here and leave it on. This picture shows you individual atoms on the surface of a material, and we'll talk more about that later. These little black dots are atoms. One thing you'll notice right away is that the atoms are organized in regular patterns, and that is very typical of materials when you look at them in detail. And that's actually very important. It's a way that atoms are arranged that makes the big difference between materials. For example, there are only 92 elements, only 92 types of atoms that are actually stable. And yet there's a tremendous diversity in the world of things and objects and so on, and much more than 92. And so the differences of all these things is to do with the way the atoms are put together and how they join together. For example, a chemist friend of mine gave me this example. This molecule, hydrogen, carbon, nitrogen, is hydrogen cyanide. It's one of the most deadly poisons. You certainly wouldn't want to have any around, and I decided not to bring it in to demonstrate. However, if I simply change this to the following, I hope I got this right, by adding that, instead of the hydrogen, I put this carbon with 3 hydrogens. That is called acetonitrile. It's a pretty harmless material used for cleaning things. So just the way those atoms are organized greatly changes the properties of these materials. And that's true of, that's just one example of an infinite number of examples. Now, this is effectively, what I'm talking about here is chemistry. It's the way atoms are arranged in small molecules. But yet what I'll really be talking about in this lecture is the way atoms are arranged in much larger assemblies, like in solids. And that's a form of chemistry. It's most commonly called solid state, either solid state physics or solid state chemistry. And I want to give you one example of this issue of the way atoms are arranged. This example I gave you already is an example that involves more than one type of atom. If I consider just carbon, carbon itself can be organized in several different ways. The end of a pencil here, this little lead pencil, you call it a lead pencil, but actually it's made of carbon, the part that does the writing. It's called graphite. This, as you know, is very soft, and that's why it's useful as a pencil. If I try to rub this piece of glass, I'm not going to scratch it. Now, the end of this object is a piece of diamond. This is called diamond scribe. You can't see it, I'm afraid, but I think you have to take my word. You'll see the effect of it. If I take this diamond and run it over this glass, of course, I can scratch the glass. The only difference, they're both carbon. It's the difference in the way the carbon atoms are organized with respect to each other in these two materials that makes their properties so widely different. All right. So, just to give you an outline of what I'm trying to say, the main focus of the talk is on the behavior of atoms in solids and what I call films, which I'll explain to you a little bit later. And basically, the general idea is I want to explain to you as we go through why do we care about this sort of thing. I've sort of given you an idea already, but there'll be more specific examples. And how do we actually see these atoms? How do we get that kind of a picture which actually shows individual atoms? And what kind of behavior do they actually exhibit that's interesting and important? So those are the three areas that I'll be talking about. So the first thing is, what is it that governs or controls the interactions between atoms? Well, atoms have a tendency to either love or hate each other. They react very strongly. It's an all or nothing situation. They often like to bond together, to stick together. And the reason for this kind of bonding is to do with the structure of an atom. Now, most of you probably have some idea about this. This is a very schematic picture. In the center of an atom is a nucleus, which is actually very small. I've exaggerated the size. And that has a positive electric charge. And then around that atom, you can think of these electrons as orbiting. More recently, well, not that recently, but in the last 50 to 100 years, 50 years, we realized that these electrons are really not well defined, but are actually like clouds. But the idea is good enough to explain what I want to say. These electrons are going around the atom. And when two atoms come together, these electrons can interact with each other and form strong bonds, or weak bonds, depending on which type of atom it is and so on. And sometimes they can repel each other and not form bonds at all. Now, there are some types of atoms there are very few atoms which are happy on their own. The only examples really are what are called the noble gases, helium, neon, xenon, krypton. These basically have electrons which are quite happy. There's an even number of electrons. In fact, there are a multiple of 8, to be precise. And they're quite happy on their own, and they don't particularly want to bond up with someone else. But when you have an odd number of electrons, you have a tendency for electrons like to pair up. And so you have a tendency for atoms to join each other and share their electrons and form strong bonds. So this is basically chemistry. And one thing I really want to emphasize to you is that, as I think Paul introduced me, I'm actually half in one department and half in another. I'm in material science and physics. And when you get into research, the distinctions between fields in many cases become quite hard to make. There are some extreme examples in physics, for example, if you're dealing with astrophysics or high-energy physics, that may be very clearly physics. But in solid-state physics, some people doing electrical engineering or chemistry have different approaches to the same problem, which are very valid and very useful to bring together. So I want to emphasize to you that although we're talking from a physics perspective, really this is not physics territory, so to speak, completely. Now, molecules are typically things that have only a few atoms. I show here water with 2 hydrogen atoms and an oxygen atom that most of you probably have seen. The distinction I want to make today and what I'm interested in is much larger numbers of atoms, trillions and more than that. Solids such as a grain of sand that contain 10 to the power of 18 atoms, which is so many zeros I don't want to write it down. Those solids are also bonded together, but you don't think of them as molecules. It's purely a definition. You think of them as something different. And although it's exactly the same issue that's going on, it's bonding of atoms that's going on in these things. So let's bring up an important distinction. Here is a critical, if there's some basic ideas that I'd like to get across that maybe you haven't been aware of before, this is one of them. It's a difference between the type of bonds atoms form. Some atoms like to find bonds which don't care which direction they point. I call them non-directional. And other atoms won't accept that. They need very directional bonds. Their bonds must be at certain angles to each other. Now, it's typical that metals are of the first kind. Metals are atoms which don't really care too much which direction their bonds form. The reason why this is true is that metals typically have only one extra electron, which is quite loosely attached and is quite happy to go in any direction to find partners, if you like. And those electrons are free to move around, and that's why they're metals. They conduct electricity by electron flow. Whereas semiconductors, which, if you're not familiar, you've probably heard of the semiconductor industry, the whole basis of computer chips and so on. But semiconductors are sort of half metals, half insulators. They don't conduct electrical current very well. Those materials, which I'll talk about quite a bit because that's one thing that interests me, have very directional bonds. And the electrons tend to be fairly tightly organized in particular directions, and that's in fact why they're not good conductors, because those electrons are not free to move around as much. So let's talk first about these directional bonds, non-directional materials, metals. And to do that, I can give you some examples with billiard balls, or actually, I couldn't get enough billiard balls, so I've got ball bearings. It would have cost $1,000 to get the number I wanted, so we stuck with something smaller. These ball bearings you're going to think of as metal atoms, and I'm going to demonstrate some basic ideas with them. Now, I'll show it to you first on the view graph projector. There's a couple of them. Now, the thing that I want to first get across is the tendency for atoms to order and form patterns. Those patterns are called crystals. That's what a crystal is. It means an ordered arrangement. Let me throw down a bunch of atoms here on this. Look at that. If I shake it, I can make it even better. I'll make it my little ruler. You'll notice that that pattern of balls is quite well ordered. Come back that minute. Oh. Do you see how look in this area here, do you see how these balls are, these ball bearings are extremely regularly organized? In fact, if you look at this little pattern, you'll see it's a hexagon shape. If you take any one of these, you can't see, in a minute I'll put it over here on the camera, you'll be able to see better what I'm trying to show, but you'll notice there's nice lines of balls, occasionally there's a defect or a mistake, but generally the balls are organized in a very regular way. It's just the same way that you would organize pool balls if you're setting up a game pool or billiards, depending on what you like to play, in a little regular arrangement. So if you play around with these things, you'll find that they tend naturally to form these ordered arrangements, and that's exactly how metal atoms behave in a crystal. So let me move this over to the camera here. Now what you should be able to see them now on top of the, there you go, look at that. You're looking at them up here and up here, just with a camera so you can see them more clearly. You can make out that without much effort, I've made a pretty perfect crystal of these ball bearings. Now, I'll show you a picture of that on this view graph. This I would call a two-dimensional crystal, because as you can see, it's just a plane, one layer of atoms, of ball bearings, whereas you can imagine in a real crystal there's atoms in all directions. So we'll come to that in a minute. This is what it looks like. It's got a hexagonal arrangement. That's the most densely packed arrangement you can make for these billiard balls. And the top view and the side view are shown there. I wonder if I want to dim the lights, or is that going to spoil that? No, you can still see. Let me explain one thing here while I've got the balls on the table here. Oh, wrong one. If you pour these in quickly enough, and it's actually quite hard to do this with the ball bearings, but I'll try it, you don't find the arrangement is ordered. You can imagine if you're thrown down the table, initially they're not going to be ordered. You have to shake them around a little bit to order them. Let me see if I can get that to work. Again, I'll try it on the view graph projector. I'll take a few more off. Actually, without me doing anything, you can see the ones near the top here are not very well ordered. In this area here, they're well ordered up here, but they're not so densely packed and ordered there. If I, on the other hand, shake it and press on it, I can get them to line up, or at least pretty well line up. There, look at that. Now, shaking is the effect that temperature has. I don't know if you've come across this in your studies, but temperature really means things that are hot, the atoms are vibrating. Things that are cold, the atoms are vibrating less. So what it takes to actually make this happen with atoms is to heat the thing up, and that's how you make nice crystals. But if you didn't do it, you get this disordered arrangement, which I showed you before, which is called a glass, or an amorphous material. Now, a very classic example of a glass is glass, like this. This is, in fact, a material which, if you looked in it with a microscope, would have a disordered arrangement of atoms like that. The reason it happens is because it cools fast enough that the atoms don't have time to organize as it comes down from the liquid state. You can find this effect out in the following way. I'm going to take a crystal here. This is a piece of silicon. A silicon wafer, in fact. I think if I put it on the TV here, I get it to reflect nicely. You can see it. This is a silicon wafer. You break this up into chips, and the chips are used to make computers. That is a perfectly ordered, the whole thing, and all the atoms are lined up beautifully across this wafer. If I break it like that, you'll notice that the edge of the break is very sharp and well-defined. You've broken it pretty much along one of those lines. You can imagine if you're going to break it, it's going to break along a line of atoms. It makes sense. Let's take glass, and here I need a volunteer from the audience. Okay, you've already done something. How about you? And you come down here. We can do some serious stuff here. So give you this hat. We're going to break a piece of glass here, wrap it up. Here it is. We wrap it up in this little piece of, let me see, better to put the other way around. Here we go. And I'd like you just to stand on it. That's all it takes. With your heel. Well, just to tap it. Yeah, you did it. Okay, thank you. I take your, good job. This glass breaks in a very different way. I hope. If I can get it up without contaminating the table. Let me take a piece and lay it on the view-graph projector. Notice the glass is transparent, as you know, and the silicon is not. You see the difference in the way it broke. The reason is there was no regular arrangement of atoms in order for you to break it so nicely. Now, you can make glass break that way if you scribe it with a line and give it and tell it where you like it to break. But in general, it doesn't have a built-in ordering. It's not a crystal. And that shows up in these properties. Now, this gives you an idea how people could figure out that atoms were there even when they couldn't see them. All kinds of properties are affected by the way atoms are arranged, the shape of crystals and things of that kind. Okay. Put my balls over on the table again. All right. Let's go on to 3 dimensions. And that's where we need the TV, really, to show this. In 3 dimensions, hope you can see this. I'll turn the lights down again. You now are going to stack billiard balls, which are metal atoms, on top of each other. And if you try this experiment, I recommend you actually try this yourself if you can get hold of any marbles or anything of this kind. You can find this out. You'll find there's actually 2 ways to do this and make a regular arrangement. And the first one is shown here. And I think you can, let me see if I can pour some. The idea has got to do with how you put the next layer on. Okay, here's my first layer of pretty good crystal here. You can see it's nicely lined up because I wasn't very hard to do that. Now let me take some extra atoms and put them on top. You see they're naturally going to go in these little holes that exist between the... Can you see that? Okay, here's where I think I need my little light. Is that coming across properly? I think you can make out the general idea, and I have the drawing on the board there that shows the same thing. This second layer of atoms, you have 2 choices about how you place them. Look at this drawing here. You see that actually, if you look on top of that first layer, I guess I have to bring that back, sorry. Show you. Oh, well. Okay, here it is. If you look on top of this first layer, there are actually 2 places you could, there's a place right here where you could place a ball bearing, or there's another place next to it. And you can't place one in both of these because they're too close together. If you place one here, the next one has to go here, and the next one has to go here, and so on. You really have to try this. It's very easy. And later on, you can come down to the front and try it if you wish, or do it at home. So there are 2 choices for the way you stack them. And if you do that and play with it, you'll find you get 2 different types of crystal structures. The first one is the one shown schematically here, which actually has a 3-layer stacking. The atoms in the 3rd layer are identical to the ones in the bottom, but the first 2 between are different. And this stacking actually turns out to be a cubic structure. This is a very interesting, if you're interested in mathematics, you might want to look at this or read about this. I could give you some references. If you make an arrangement of these atoms, you'll find that they actually possess, even though they're made of hexagonal arrays, they actually possess a square-looking symmetry when you look at them in the right direction. And this is called a face-center cubic structure, and it's the most common structure of metals. Copper, gold, aluminum all fall into the FCC structure automatically. When you cool down a molten piece of aluminum, just like these billiard balls or ball bearings, it comes down into the arrangement that we saw here. There's a related structure called the hexagonal close pack structure. I won't say much about this, but this has a 2-layer repeat. You basically go back to the same, you start with this one, you go to the one position, and you go back to the original position. And this is called the hexagonal close pack structure and doesn't have cubic symmetry. And it's not very commonly found, but it exists in metals like cobalt and cesium. Now, I just want to say a little bit about this science of crystallography. This science of figuring out how atoms are arranged is called crystallography. It's a sort of branch of physics and chemistry. And crystallography is really heavily reliant on mathematics, because mathematics can be used to predict all the allowed possible ways you can stack things and fill space. It's the same thing as tiling your kitchen floor. You can't just take any shaped tile and do it. It won't work. There's a lot of limitations on the size and shape of tiles. And that whole science is a fascinating branch of mathematics, which has great practical importance. And even today, there are still innovations being made in this field. It's both, I've given some examples in the text you could look at. I won't go into them in detail now, but of where it's important. Let me now talk about silicon, which is a semiconductor, which I'd really like to focus on mostly. And silicon isn't quite as simple as these billiard balls here, because the silicon atoms have these directional bonds. There are 4 electrons per atom, and those 4 electrons, like, as you can see, I think, fairly well in this model here, and I'll put it on the camera in a minute. This is a model of the structure of silicon, and if you look at one unit in this model, put it on the camera for you. It's a little bit too small. I think you can just about see if I can get the right one in here. Yeah. Inside this model, if you point at an atom, can't see if I got it. The yellow atom there in the middle has 4 bonds pointing in different directions. You can see 3 of them more or less straight on, flat on, and the other one is pointing more or less in the direction of the camera. These are what we call a tetrahedron. If I pull one of these things off, I think you'll be able to see it much better. Here we go. This is a tetrahedron. Here it is. And lay it down here. Okay, you can see it quite well. The silicon bonds like to have this arrangement. By the way, carbon has exactly the same preference, and that's the structure of carbon in diamond is identical to the structure of silicon, so you'll see I refer to it as the diamond structure. So it has very directional bonds, and this directionality means that the structure in which the atoms are arranged isn't quite as simple as these ball bearings I've been playing with, because they have to satisfy a constraint that they want to point, the line between atoms is pointing in a particular direction. And I've shown you a drawing here of the structure of the silicon crystal with one of the tetrahedra highlighted in red, so you can see the way that the atoms are arranged. Now, as I tried to say before, the consequence of these directional bonds is quite important. For example, you can imagine that in metals, because the bonds are non-directional, it's easier to move the atoms around. And as a result, most of the things that you use for what we call structural materials, like your car or an airplane, are made out of metals. They're not made out of diamond. And it isn't because diamond isn't very hard, but diamond is not very flexible. The atoms don't move around very easily, and it'll just break. It's very brittle. So you want something where the atoms can move easily for things like aircraft wings that are going to take a lot of forces up and down. That's why you also want something which is quite light for an aircraft. So that's why metals are so widely used in structural materials. On the other hand, silicon is quite brittle. I mean, I showed you already, this piece of silicon can just be broken. You could not do that. Excuse me for the mess. You could not do that with a piece of metal. It would just bend of the same thickness. A piece of aluminum would just go bend. The reason is because of this very directional arrangement of atoms, which is not flexible. Now, I want to talk about the surface in particular of silicon, because surfaces are something that I'm particularly interested in. And what you're looking at with a microscope here is the surface of a material. The surface is just the outside. It's hard to get into the inside to see the atoms, but you can look at the atoms on the outside. And it turns out the surfaces are actually very important for reasons I'll come to in a minute. So what happens at the surface of silicon? Let's look at this bottom picture here, and we'll see if we can understand what's going on. You'll notice that when you cut this crystal, you have bonds which are not satisfied. You've broken bonds. And those bonds are called dangling bonds for obvious reasons. Those dangling bonds aren't very happy. Atoms don't like to have no bonds with somebody else. That has a high energy, and it's not favorable. You can see that, I think it's not going to show it well on the camera, but later on you can come down and look at it. I have a model here of the silicon surface. Put the lights on. This model of the silicon surface shows these atoms which are drawn in the sketch with their bonds pointing up that are missing. There's no atom here to satisfy these 2 dangling bonds. Now, I want to try and explain to you what happens on the real surface. If you make a surface like this and it's very clean, And that's an issue that's not easy to achieve. But if you make it very clean, the atoms will rearrange themselves to try to get rid of these dangling bonds. And that's called a reconstruction of the surface. So that's the first thing I want to show you, because we see it in the microscopes. And here is a picture of the reconstruction. Now I'm going to explain it to you by getting some volunteers to come down to the front here. And I need quite a large number. In fact, the whole first row, if you don't mind, could come down to the front and stand and face the audience. I want you to stand like this. You're a silicon atom on the surface. You've got two bonds. You don't have to do this with your legs, pointing down like this. And you have two bonds which you're going to stick out your hands like this, pointing in this direction. So line up so that you're just touching each other's hands, but your arms are pointing up like this. So space yourself out enough. So you've got to space out. You have to move down quite a long way. I want you to put your arms up like this and space you so you're just touching. We've probably got more than enough, actually. Let's get rid of the last... There's probably too many. Can we get rid of the last two people? Sorry about that. You can lie on the bed of nails if you wish. No, we need you. Okay, now space out. Now, okay. Could you stretch it, be far enough apart that you're just touching? Okay, now I want you all to move a little further apart so that you move down here a few feet. So you can't quite touch. Move further. Paul, yeah, I need your help here. Come along so you're not quite able to touch. Not quite able to touch. You guys have to, you can't quite reach. Move down that way. Okay, the last one we probably... Right, now here are these silicon atoms on the surface in a chain with these two bonds which are not satisfied, and they can't quite reach each other. So what's the natural thing they're going to do? You lean over and hold hands, both together. Lean over quite a bit. Okay, now you can't reach him anymore, right? So you have to lean over to her and hold hands. And you lean over to him. Now you can't reach her, so you're going to lean over to her. Okay, and I'm afraid you're left at the end there. Story of your life, I'm sure. Now, what's happened here, could you keep your hands together? If you look at this structure, it's now got, all the atoms are now, originally they're all identical, by the way. These guys aren't identical, but silicon atoms are actually identical. But supposing these guys were identical, they're not identical anymore. This guy and this guy are pointing together, and then there's a gap, and this guy are pointing together, and there's a gap. So it takes, instead of repeating every one atom, which it was before it reconstructed, now the repeat distance is 2. The second atom is identical to this one, it's identical to this one, and so on. So it's paired up, if you like. And this reconstruction has doubled the spacing on the surface. Okay, thank you very much. I hope that made the point. So this is what's shown in the picture here, that after the atoms have moved, they've created a doubling of the period on the surface. And that's what's shown also in this model, which again you can look at later, in which you'll see that the atoms have moved together and paired up, and then the next one has to move in the opposite direction, and the repeat distance is now twice what it was. That's called a 2-by-1 reconstruction because of the doubling of the period in one direction. Now, I'm going to show you a real picture of that. It's the main reason I went to all that trouble. This is what it looks like. By the way, I have to thank David Cahill from the Materials Science Department for all these beautiful, many of the beautiful pictures I'll show you. Taken with a scanning tunneling microscope, which I'll explain in a minute. That picture shows that reconstruction of the surface. Notice that these bright blobs, which are single atoms of silicon, have kind of paired up. So here's a pair that's close together, then there's a gap, and then a pair that's close together and a gap, and so on. So that's a direct image of that reconstruction of the surface, which occurs because of the desire for bonds to join together. Electrons like to pair up and form bonds. So that's called a 2-by-1 surface reconstruction. That's what you see if you look at the surface of clean silicon. You, by the way, won't see that if you look at this surface because it's covered in rubbish. On the atomic scale, it's got thousands of layers of garbage. Stuff from my fingers, the oxygen in the air, and in order to get this kind of clean surface, you require to clean this in a very good vacuum. Okay, now, why do surfaces matter? And the reason that really that they're most important is because of what I call thin films. Now, what's a thin film? Time for my breakfast. If I take this, this jelly and spread it on some bread here, I'm kind of hungry anyway. I can make, I'll show you this, make myself, actually, you'll notice that there's now a layer of jelly on this, a very thin layer of jelly on this piece of bread. That's a thin film of jelly. It's got a thick piece of bread, and I spread the jelly very thin. The sandwiches you get when you grow up in the United Kingdom tend to be made that way, with extremely thin films of using very... whereas America is overstuffed sandwiches, you can't even, you bite in and they come flying out the other end. Cultures are very interesting. Anyway, thin films are very important, not just in the sandwich industry, but actually in the real world, because every computer chip that you look at, it turns out that the computer chip itself is just on a very thin film on the surface of a piece of silicon. So if you were to look at a computer chip, which is made out of this kind of silicon that I broke for you, you would find that if you looked at it with a microscope, magnified the thickness of the silicon, the actual devices that make the chip work are very tiny, thin films on the surface. If you want an analogy, think of it like the device is like the beach area, and the substrate is like the United States of America. So it's only in California that anything important is happening in one of these chips on the beach. Everything else is just there to hold it up. And that's the way it is with a computer chip. Now, why is that? Well, it turns out that you can control the types of atoms you put down on a thin film very well, and you can make ordered structures in which you put one atom in contact with another, and that's how you can make these interesting devices that make computers, for example. Here's an example, this is a picture of my own, that shows you the atoms as they're arranged. This is a silicon crystal, looked at very high magnification, edge on, and on top of it is a film of glass, SiO2. And this interface is the boundary between these two layers, is in fact the most important part of a transistor or computer device, memory device. This interface and its properties are the reason, in fact, why silicon is the main semiconductor that's used in the semiconductor industry. This is where all of the action goes on in computer chips, this interface, which is defined by just a few atoms, if you like. And it's made by putting this thin film of oxide, silicon dioxide, on top of silicon. Let me explain a bit more about why that's important by giving you a general idea for the way in which a field effect transistor works. This is, in fact, the elementary device which is used both in memory and microprocessors in computers. It is based on the field effect transistor, sometimes called the FET, and it's based on metal oxide semiconductor, so it's sometimes called the MOSFET, or the MOSFET, if you're into the electrical engineering field. This device works in the following way, very conceptually. There is a source of electrons, think of it like a source of water, if you like, which is current, and there's a drain. In fact, I was hoping to set up a demonstration with water, but we couldn't quite get it together. But you could do all of this with water. Source and a drain, and of course the current flows from the source to the drain. The device is on or off depending on the voltage applied to this gate. The voltage, you put electrons on the gate and they put a force on the electrons in the semiconductor, and that force can switch on and off the current flow in the source drain, between the source and the drain. And the attraction is that you can put a number of electrons on the gate and leave them there, and they will keep effectively a memory. In other words, if you try to find out later, does current flow or does it not, that could be equivalent to saying, is this a 1 or a 0 in a computer chip? And the answer depended on whether you put charge on that gate, if you like. That's how memory works. You can also use it as a transistor to amplify signals, because small changes in the number of electrons on the gate can change large currents that flow between the source and the drain, so it's called amplification. I'd like to just tell you a little bit of history. At the University of Illinois, John Bardeen, sadly died a couple of years ago, I guess last year, was one of the inventors of the transistor, had been here, and he was also, when he invented the transistor, he was at Bell Labs. And he's one of the few people, I think, if not the only person, to have won 2 Nobel Prizes in the same field in his lifetime. And one of them was for the invention of the transistor. And in fact, the transistor he invented is called the bipolar transistor. And if anyone's interested, I could talk to you later and explain more about what the differences are. The field effect transistor was actually invented before Bardeen, but could never be made. It was invented in the 30s, and whereas the bipolar transistor was invented in the 50s, late 40s, 50s. Furthermore, the field effect transistor is the dominant transistor in the whole industry now. The bipolar transistor invented by Bardeen, in fact, is not used very much at all. The problem with the field effect transistor was to make such a perfect interface that current could flow in this way. And it has to be very perfect without any places that can trap electrons. And this is something that people discovered by accident is easy to do with silicon, but was not easy to do with the other semiconductor called germanium that was used before. However, Bardeen is was an amazing man, and apart from winning these 2 Nobel Prizes, it turns out that he predicted effectively the theory by which it was possible to understand why these transistors never worked before. So he actually contributed a very important way to understanding the properties of this interface in the field effect transistor. All right, so I'm trying to explain to you why it's important to look at these interfaces and surfaces in semiconductor devices. The light, I think I need it now, actually. Just when you... Okay. I'd like now to talk about some of the properties, we haven't got too much time left, about 15 minutes or so, about some of the properties of atoms on these surfaces and how you grow these thin films. And you can imagine you grow them by depositing atoms. So you just basically, I'm going to spill them, I'm sure, but you basically drop atoms onto a surface. And if the temperature is high enough, they move around. They're free to move around, and they can organize themselves into these nice regular crystals. One of the intrinsic things you can imagine to see on the surface is maybe shown here. We're not getting quite as good a picture as I did yesterday, just by chance, but let's see if I can get it. Anyway, the graph over there shows it very well. You can make it out here at the front. There's a what I call a step. There's a layer down here, and then there's a layer that's higher up here, and along the boundary is a step. That step is 1 atom high. There's a picture of it that's much easier to see graphically. You expect to see a lot of steps on crystal surfaces because nobody knows how to grind them flat enough that there are no atomic steps over the whole size of a piece of material. So you have a large number of steps on a crystal surface. That's a very important aspect of crystals, which I'll come to in a minute. Here is a picture of steps on a silicon 100 surface. So here, 100 is a terminology that is used in the industry to describe the direction in which you've cut the silicon surface. It's a generalized coordinate that points in a certain direction. Notice now these beautiful steps. You can make out this 2x1 reconstruction. These little pairs of atoms are very small now, but you'll notice that there are different layers. There's the lowest one. This whole one here is the next height, and this one over here is the highest. And you'll see the steps or the boundaries between the two. And one thing you might notice is that one type of step, this one here, is kind of rough, whereas this one over here and this one over here are actually much better defined, and they're actually different structures, those two steps. So you can visualize these steps in the electron microscopes. So let me talk about the microscopes for a minute. How do you see these kind of pictures? Well, there are several types of electron-based microscope that are used to see them. I myself work with a technique known as electron microscopy, which I've showed you some examples, but I won't explain that because it's somewhat more complicated to understand. Instead, I'm going to talk about the scanning tunneling microscope, which is a very new and very powerful technique, which is used to take that picture over there. And that's much easier to understand. But I will show you a picture of my electron microscope before I go on to that. This is an image of it to show there's a rather complicated bit of equipment. Now, when you look at a picture like that, you've got no idea what size it is. So you really need a scale. So I asked my collaborator here, Dr. Barbie, to get up onto the microscope, and I hope you can see her right here. There she is. So now you get an idea for the actual size, this overwhelming size of this instrument. And I want to thank my daughter Margaret for lending me her actually it's Nurse Barbie. You know, it's really shocking. I mean, the toy industry is 30 or 40 years out of date, and there's no such thing as Dr. Barbie available. And I hope that the young women in the audience won't be deterred by this social stuff, because there are tremendous career opportunities in sciences for women. And just because society is sort of a little backward on television and in toy stores, don't let that put you off. I want to tell you a story, actually. I found out that there's an organization called the Barbie Liberation Organization. And I'd really like to join it, but I didn't actually get the address. These guys go into the stores around Christmas, and they take Ken dolls and Barbie dolls that have voices, and they swap the voice boxes over and put them back in the box and package them to be sold at Christmas. So when the children take the Barbie out of the box and switch her on, she says, "Eat lead, snake." And when they take the Ken out, he says, "I think I have to go to the store and get a new outfit." So I think they're really raising some interesting challenges to social perceptions with this brave act that they're going through. I hope it has some effect. All right. Let's talk about the scanning tunneling microscope. This is a very simple concept. And in fact, I think many people never believed that it would work. And somebody was brave enough. This is actually one of the things you find in invention, that it's often good if you don't know what other people have tried to do. You don't know they tried and it failed, and they wrote long papers saying it could never be done, because you did it and it worked. And that's in the nature, a lot of science is done that way. A lot of luck is involved, serendipity we call it. And this is the case with a scanning tunneling microscope, which was invented about 10 years ago. And basically, it's very simple. It has a sharp tip that scratches around on the surface and kind of feels the surface. Let me show you what it means by using a phonograph. Now, these things are getting kind of out of date, but I think you've probably all seen these things. This record player here, they play albums like this. What these things actually have are scratches, grooves that go around. This is one I don't really care about destroying. Grooves that go around the outside, and the phonograph's job is to feel the surface of this groove and to make a sound that depends on the position of the surface. So it's actually, in a sense, a microscope that looks at this groove, which you can barely see with your eye, and magnifies it acoustically in a funny way. Let me show you how it works by taking a simple example. Here we've got a little phonograph. I'll switch it on. Oh. I'm going to, I have here an old-fashioned, in the original phonograph, some of you may have seen, they were very simple. They just had a cone like this and a needle, and the sound just was naturally amplified. Let me take a piece of sandpaper, emery paper, and put it on this phonograph here, switch it on, and let me lay this little thing on here. You can tell that that's a rough surface. This needle is responding, going up and down, and it makes a sound which is coming out through my microphone. Let's try the other side of this sandpaper, which is a piece of paper, which is medium roughness, I'll say. Much smoother, right? You're getting an audible picture of the roughness of the surface. Let's take it off altogether, and we have a very highly polished piece of some metal with a ceramic film on it. This is very flat. Oh. So you've just been doing audio microscopy of surfaces using a phonograph. If you extend that idea to making a picture of the position of the surface, which isn't hard to do electronically, you can make an image, and that's what that image over there is. The tricky part is how do you move the tip around over very tiny distances on the scale of an atom so that you can map out the shape of the surface. And as I say, that's the kind of thing that nobody really would have believed was possible, but it turns out you can do it with what are known as piezoelectrics. Piezoelectrics are crystals. When you apply a voltage, they move. And in fact, they're the kind of crystals which are used in the old-fashioned needle detectors. And those crystals, if you apply a very tiny voltage, you can move them a very tiny distance. And so you can reproducibly move things on the atomic scale with those kind of crystals. And as long as you build a very nice, stable system, you can make a microscope. Now here's a picture of the tip of that microscope reflected in the silicon wafer. This is from David Cahill. The tip is very sharp. It's almost atomically sharp. And you can see it here, obviously at very low magnification, is this, at the end of this point. And the reason for the reflection is that it's standing right next to a piece of silicon, which is giving you a double image of it. This is more or less as it's imaging. And what the guy is doing is going to scratch the tip over the surface and record the height of the surface as a function of position and make an image like that. Now, in fact, you don't touch the surface. This is the kinky part. The name of the technique is scanning tunneling microscopy. And scanning microscopy would be enough to explain what I just said. You move around a tip. Scanning is the motion of moving around. But tunneling is the trick. You don't have to touch the surface like I did over there. You can bring the tip very close, and electrons can jump across the gap, and you can measure that current without actually touching. And that jumping across the gap is known as tunneling. So it's a non-destructive technique. It doesn't actually require you to hit the surface because you would destroy it, of course. Okay, we're getting near to the end here. I'll just show you some more pictures. Here's a scanning tunneling microscope image that shows a mountain, if you like, sitting on the surface of silicon. This is a piece of dirt. And if you search these silicon wafers hard enough, you'll find there are lots of pieces of dirt, even though they're made under the most clean conditions that anyone can imagine. I don't know if any of you have come across the word clean room, but if you go into a semiconductor factory, you'll discover they have clean rooms. And they describe a clean room by a class. And the class has to do with how many particles are in the air per unit volume, so let's say per cubic meter. Typically in this room, there are probably trillions of particles of rubbish floating around in the air. I mean, a lot of them come out of my mouth, for example. But in a clean room, nowadays, they've gone down. They started with class 1,000, which meant 1,000 particles of a certain size per unit volume. And that requires all kinds of complicated filtering equipment. Everyone has to wear dress over them and so on. They're down now to class 1, and even lower than that. They're down to less than 1 particle per cubic meter of air. And to do that requires literally hundreds of thousands, millions of dollar equipment per small room. So that's one of the reasons that semiconductor fabrication is very expensive. And the smaller electronic devices become, the more difficult it is to keep them clean. These particles, like this little one here, is so small you'd never see it. But it's big enough to cause problems on the surface of the silicon. Okay, one of the other pictures I want to show you is to do with growing 2 different types of material on top of each other. This is called epitaxy. And it's also very important. It's something that I'm particularly interested in. Epitaxy is when you add atoms of a different kind onto a surface and hope that they will adopt the same arrangement as in the crystal. In other words, you can make them arrange themselves in a way that they wouldn't normally arrange themselves in because they're sitting on top of an ordered arrangement of another material. And this is a picture I took with my microscope that shows you the silicon atoms arranged in a little square array. And on top of that is a different material, metal, called nickel disilicide, which has arranged itself with the same structure and made this very perfect interface on the atomic scale. This turns out to have very interesting properties, and you can think of new types of electronic devices that you can make with this sort of structure. You see, the whole basis of the semiconductor industry for the last 10 years has been shrinking the same kind of device down. It's the same old MOSFET, MOSFET. It's just getting smaller. The difference between a Pentium and some old 8086 chip that came out in the IBM PCs when you were all about 3 or 4 is just the size, literally, of the transistor. By making it smaller, they can make it faster, and they can put more of them on a chip and get more memory, more speed. But that's going to run out of steam at some point, maybe 10 years down the line. You make these devices small enough, they're not going to work anymore. You have to have new types of devices that will do new types of things. And that's one of the areas that I'm very interested in, looking at novel materials for making electronic devices that would basically have the same properties. They'd act as memory or switches, but they would be able to be much smaller and much faster. And there are a lot of interesting ideas for that based on this kind of technology. All right, let me see. I can skip some of this because we're getting near the end here. You can read through. I'm skipping a few view graphs ahead here to show you. You can read through this later if you like. To show you the general idea of what you're concerned about in growing these layers is getting perfection, is getting uniform films that are nice and regular. But when you drop atoms onto a surface, where did I put my ball bearings? Here we go. When you drop atoms onto a surface, you can do that in several ways. If you've ever grown, some of you guys may have grown crystals with a crystal kit you can buy from the store for $10. And you do it, you don't need a kit, you can do it with household stuff. You do it from solution. You dissolve something in water, and you sit there and wait, and it comes out of the solution and makes a crystal on the bottom. What's happening is you've got a crystal like this, and the atoms are coming out relatively slowly from solution, and they have time to move around and find and stick onto these step edges and allow this crystal to grow like that. They fall in the wrong place, but they can move on the surface. That motion is called diffusion, and they can grow this nice regular crystal that way. But solution growth is only one way of making crystals. In the area I'm interested in, these crystals are grown in vacuum. They have to have very clean surfaces, and liquids tend to be rather dirty. So instead of using solution, you use what are called beams of atoms. They're called molecular beams, but they're typically beams of atoms. And these are, if you like, little jets of atoms that come firing out of a hole in the side of the chamber, more or less exactly like I do, and they're dropped one by one, if you like, onto the surface. And you can put down a certain number of one kind, and then you can switch that one off and put another certain number of another kind. And that technique is known as molecular beam epitaxy. And that's, in fact, how that layer over here was grown, shown over there. So when these atoms fall on the surface, they form what are called adatoms. They fall in the wrong place, but it's favorable for them to move around on the surface until they join up with some existing little island, as it's called, is shown over there, and make a crystal. And it's this kind of growth which leads to the best quality crystals. Here you see a picture in the scanning tunneling microscope showing these islands. This is germanium that's been put down on silicon, and you'll notice that the germanium is forming these little triangular islands on the silicon. And if you grow slowly enough, the atoms will stick to these islands and make nice uniform layers. So the ideal way of getting crystals to grow is to have, don't try to follow me because I'm going to miss out a few of these view graphs, about 4 or 5 down, is to have the atom attach itself to a step. And in fact, when it attaches to a step, it actually attaches to a little, what's called a kink in the step. It likes to attach itself to the position where there's a little edge between this step here and this step here, and as that atom's attached there, that kink moves across, and as that kink moves across, the step moves in this direction. This method of growth of crystals is called step flow, and it gives you the best quality crystals, and you're always trying to achieve this when you do this kind of crystal growth. The problem is, it's difficult to achieve in practice because you have to, these atoms are going to land randomly. You can't tell them to go there. You fire them off, you've got no control over where they go. So you have to allow them to move around on the surface. And they move around, the higher the temperature, the more they can move around. So you like to increase the temperature while you're growing it. However, it's not quite that simple because when you increase the temperature, they can do other strange things, and that's the last thing I want to show you. And that is they can form these blobs. And the reason got to do with the basic thing that you see every day when you look at your window in the rain, that some types of material don't wet other types of material. The word wet, you all know what wet means. Actually wet, like all science, science always invents new meanings for common words and confuses everybody. Wetting in science is a very specific thing. It means, does something like to form a nice film on the surface, like I spread the jelly, or will it ball up into little blobs? Now, if you pour water onto glass, you know that it forms little balls, little blobs or droplets of water. It doesn't like to wet. The reason is that the water atoms don't like to join up with the glass atoms, so they'd rather make little balls where they have the minimum contact. And that's what I'm showing you here. This is a disaster if you're trying to form a nice uniform film of water on glass and you end up getting all these little droplets. Sometimes it's desirable for a raincoat, you don't want a nice uniform layer of water. But in crystal growth, it turns out that if you go to high temperatures, almost everything doesn't, it's very unusual that something wets the substrate. It usually likes to form blobs, and if you give it enough motion, it will form these large blobs and not a nice uniform film. So you have to play a game where you give the atoms enough mobility to move a little bit to form the step flow, but not enough mobility to ball up and form these blobs on the surface. And I have a picture of this balling up taken with the electron microscope somewhere here, and this will be my last picture. This is a picture of a picture taken from above of a layer in which you can see, if you like, these little droplets. They're funny shape, but they're droplets of a metal that's been deposited on silicon. It doesn't like to wet the substrate, and it's formed these little isolated islands that will never join up and will never make a nice continuous film. So you could never make a field effect transistor out of a layer like that because you wouldn't have a continuous layer there and a continuous interface. So really, that's all I want to say. Let me just summarize my talk with a concluding view graph here. I didn't get through everything, but if you're interested, there's a few examples that are in your notes you could look at and read some more. Basically, what I tried to get across to you was that the social behavior of atoms, how they behave in groups, is very important, and it's also very interesting, I think. And you know, science is done, usually you're always trying to argue both of these things. You don't do it if it's not interesting, but you also don't get to do it if it's not important. So. And you can see it with these powerful microscopes. You can see individual atoms, and that's something that's only been possible in the last sort of 10 years. So a whole lot of new stuff. There's an awful lot that's not well known about what really happens, and there's a lot of science to be done. We have some control over it, and I want to show you, I do have one more view graph I'd like to show you, and I got it from a guy at IBM Research in Almaden, California, and it is an example of something quite novel. Can you see that? What this is the guy has taken his scanning tunneling microscope tip and he's used it to shove atoms around. Unfortunately, no microscope can look at something without disturbing it anyway. You're always very close to it and you exert some forces. And people in this field have discovered that you can actually push atoms around if you're not careful. Well, his aim in life was to deliberately push atoms around. The first thing he did was push them around to form the words IBM, and that appeared on the front page of the New York Times. It was the smallest ever writing that anyone had ever done. Single atoms. If you can write a letter like IBM, these are individual atoms of xenon, on this scale, you could write the whole Library of Congress onto one little piece of silicon this size, because there's so many atoms. So clearly that's the ultimate of what you could do in terms of density of information. The problem is how you're going to get in there and read it. and it would take you a million years to write it. So we haven't got the technology, but there's all kinds of possibilities around in the future. What he's done here is he's made this quantum corral, he called it. And the quantum corral, you can see the idea, it's a corral like the OK corral. It's got a little ring of atoms around. It turns out it shows some interesting physical states, which are shown by these waves that you see in the structure. The main thing I want to emphasize is he can make structures on the atomic scale by pushing atoms around. In principle, this is the ultimate, and one of the things you'd also like to do in these experiments is to actually control where atoms go. So you could make devices that are so small, you could imagine packing them that densely onto an integrated circuit so you could achieve the storage capacity and the speed and other things that you want. But this is still way off in the future, and a tremendous amount of research is required before anything like this can really be done practically. And at the moment, though, there are many, many useful devices that can be made, devices being in the semiconductor area, for example, from these thin films. And these microscopes are very powerful in giving you information that allows you to understand how to make better and well-controlled structures. So at that point, I'd like to finish, and you're welcome to come down. You're welcome to ask any questions. Thank you for your attention.